Welcome to the fourth day of this quantitative course, and today we have correlations. So without any delay, let's just go right in. Okay, let's start with the classic correlations and the foundation which will lead to the linear regression, and this will also a little bit helps to understand what that is. And for this example, let's think about if researcher wants to find out is trust in people associated with the life satisfaction. There's two things which we can find out with the correlation. What is the power of the association and what is the direction of the association? Both trust in people and the degree of satisfaction with life are in the data as numerical variables. In this case, researchers should look at the correlation of the variables. And the question, of course, is what is the correlation? It's a measure of power and direction of a linear connection between two numerical variables. So you're going to use continuous variables, not categorical variables. And the correlation does not measure how much of the value of another variable changes as the value of another variable changes. So there is test for this, like linear regression analysis, but we are not going to go into that right now. We are just checking up correlations, and correlation does not indicate causality. This is really important, and of course, it doesn't measure which variable may affect either one independent variable or dependent variable, or what you're trying to measure out basically. And in correlations, we have a thing called correlation coefficient, which will describe the power or the strength of the correlation between the both variables. So the farther from zero the value of the correlation coefficient is, the stronger the linear relationship of the both variables is. And we have negative correlation, no correlation, and positive correlation. And basically, the negative correlation is the case where the correlation or the slope is downwards angle. It's a negative correlation, and we have the positive correlation, which is upwards angle. And no correlation means that the correlation line is totally flat. But I'm going to show some graphs about this, which will open this thing up better and it's more understandable. And here is the scale on the top, on the bottom, which will see how the values will change, because -1 is the full perfect negative correlation, perfect positive correlation is +1, no correlation, or the perfect equilibrium is 0. Now, here it is. This is the case of no correlation. R is 0.01 negative. It's basically not no correlation at all. And as you can see, the line is totally flat and all the distribution are blown up like with a shotgun. There is no angle of the observation or the correlation. And here we have a positive correlation. R is 0.84, and we can see how the positive correlation is when the slope is directed upwards, so all the observations are in a rising angle. As the other value increases, the other value increases too. And here we have a negative correlation, and of course it's a reverse of the positive correlation. Who wouldn't thought? The R is negative 0.84, which means the slope is in a downward angle. As the other variables, like the numbers go up, the other ones go down. So there is a negative correlation between the two variables. And here we have a special case, nonlinear correlation. Sometimes the distribution is a little bit different like this. It's the it's a non-linear, it doesn't have any straight shape, but as you can see we still calculate the slope there, and it will give pretty interesting and weird results. So in this kind of case, correlations are not your best thing to do because it doesn't measure the nonlinear association between variables. And here is the compilation of different kind of distributions and correlations for your pleasure. So there are many kinds of cases where the observation is more close to the slope and not. But then again, everything can be measured, but beware of the nonlinear correlations. But those are pretty easy to spot because scatter plot will reveal them also. So usually the correlation coefficient is calculated in a correlation matrix where there is several correlation between different variables. In a matrix, there is like a similar variables in the rows and both of the columns, and they are mismatched against each other. And most cases the correlation is just shown in the cells of the lower triangle of the major matrix or the lower triangle matrix, so to speak. And here is one of the examples, more colorful one, but it's like a stack of variables, and you can see all the correlations between those, and it measures linear relationships between variables, and the odds values varies between -1 and +1, of course, what we talked about before. And the rule of thumb here is that the weak correlation is from 0 to 0.3, moderate correlation is 0.3 to 0.6, and strong correlation is 0.6 to 1. So that's the rough scale around there. It's not that clear, but usually that's the rule of thumb, so to speak. Now it's my time to be cruel and show you how this correlation coefficient is calculated, and we are going to calculate person's correlation coefficient here, and there is the whole formula, and it's a little bit more complicated than you are probably used to, but it's not that complicated when we go through it, and I'm going to show it to you. I know this looks like a Christmas tree or something, or you have been eaten a bag of crayon and vomited on the screen because all the colors, but these little bit help on understanding what number belongs to where. So, to simplify, first, the correlation is calculated with the subtraction of x variable's value and means, which is multiplied by subtraction of y variable's value and mean. So repetition here. And these subtractions are summed to all observations in the sample. So we have the sum function there. And finally, all the sum of the subtractions are divided by the count of observations that are multiplied with x and y standard deviations. So when I have broken it up in a text format down there, it's much more simplified there, and you could understand it better. So every time when you're seeing this kind of an equation, just take the time, break it apart, and write it down, whatever it is. If you write it down somewhere, it becomes pretty clear and it's not that complicated, even if you think it would be. So, like in previous slides mentioned, we need the standard deviation and means for the calculations. So here is the example. We have just three persons variables of height and weight. So if we want to know if height is correlated with body weight, that's the one classic example we can use. And this table includes the weight and height of three people, and we need to find the key figures of mean and standard deviation here. So there's the calculations. We first figure out what is the mean weight of the people and mean height, and that's simple. We just we just sum the column cells and divide it by the number of people. And standard deviation is also just what were doing in the first exercises and the first lecture. So nothing weird about that. Just like I have been saying, if you know how to calculate mean and standard deviation, you get far because we just use these building blocks against our observations and we are going to end up with Pearson's correlation coefficient. Now, the fun doesn't end there. So, the example was association with height and body weight. So now we have the means and standard deviation of height and weight. So we are going to use those. And let's put the numbers on the equation here. And we are going to end up with this kind of a monstrosity. I know this is kind of long, but as you can see, it isn't that complicated. When you see the formal equation for with the sum function, if you haven't been used to those, you're a little bit like, what the hell is going on? But here what we all do is we take every single individual's height and weight and subtract the mean from it and then divide the whole thing with the number of people and the standard deviations of height and weight. But we do these calculations separately with every individual. As you can see, I have a mark there with the ID numbers. And we are going to end up with the person's correlation coefficient, which is really high. So they have a strong correlation with each other here. Okay, everybody, that was the correlation part. And you probably are thinking why his voice sounded a little bit different. It was just because it was last year's course and I did record every lecture one after the other, so my voice was really shot to hell. So that's why I sound a little bit weird in that, but the course also entails regression analysis, which you don't have to do right now. We streamlined it in a way that you are going to get that later on the courses. So I think Patricia McMullin and friends are going to teach you that. But next up is the demos, so good luck with those.